In the quiet laboratories of the early 20th century, the atom was still a mystery, a concept whispered among physicists who believed that unlocking its secrets might reveal the fundamental laws of the universe. No one yet imagined that within that invisible nucleus lay the power to reshape civilization itself. The journey from curiosity to catastrophe began with pure science, discoveries made not for war, but for understanding. When Albert Einstein published his equation, E equals mc2, it was a revelation that mass and energy were interchangeable, two sides of the same coin. At first, it seemed abstract, almost philosophical. But in the right, or wrong hands, it would become the equation that redefined humanity's relationship with destruction. As the 1930s unfolded, the world stood on the brink of turmoil. Political tensions grew, and scientists in Europe were already sensing danger in the rise of totalitarian regimes. In 1938, a remarkable discovery by German chemists Otto Hahn and Fritz Strassmann changed everything. They found that when uranium atoms were bombarded with neutrons, they split apart, releasing vast amounts of energy. This process, called nuclear fission, was later explained by Lise Meitner and Otto Frisch, who recognized its enormous implications. For the first time, it was understood that the atom could be broken, and that the energy released from this rupture could be far greater than any chemical reaction known to man. The discovery was revolutionary, but it carried with it a dark shadow. If this energy could be controlled, it could power the world. If it could not, it could destroy it. When news of nuclear fission reached the United States, a small community of scientists realized the stakes. Among them were refugees from Europe, men like Leo Szilard and Enrico Fermi, who had fled persecution and war. They understood that Nazi Germany had the scientific talent and the resources to turn this discovery into a weapon. Fear drove them to act. In 1939, Einstein, urged by Szilard, signed a letter to President Franklin D. Roosevelt, warning that Germany might be developing a new kind of bomb, one of unimaginable power. The letter was short, cautious, and respectful, but its consequences were enormous.
Yes, I did.
It marked the beginning of what would become the Manhattan Project, the largest and most secret scientific endeavor in history. The Manhattan Project was more than a research program. It was a convergence of some of the greatest scientific minds of the century. Robert Oppenheimer, Niels Bohr, Richard Feynman, and many others. Entire cities were built in secrecy. Los Alamos, Oak Ridge, Hanford, where thousands worked around the clock to harness the power of the atom. Engineers, soldiers, and scientists collaborated in an unprecedented union of science and state. The scale was staggering. Billions of dollars invested, thousands of workers sworn to secrecy, and an urgency driven by the fear that the enemy might strike first. The goal was singular and terrifying: to build an atomic bomb before Germany or Japan could do the same. But beyond the laboratories and production plants, a silent moral question began to grow. Could humanity truly control such a force? The scientists working on the bomb were driven by patriotism, but also by doubt. Oppenheimer himself, a man of brilliance and introspection, later recalled a verse from the Bhagavad Gita: "Now I am become death, the destroyer of worlds." In that single line, the moral tension of the project was captured. The atomic bomb was not just another weapon. It was the embodiment of mankind's ability to rewrite the laws of nature, and perhaps its own destiny. By 1945, the project had succeeded. The first test of a nuclear weapon, code, named Trinity, took place in the desert of New Mexico. In the early hours of July 16, a blinding light lit up the sky, brighter than the sun itself. The explosion vaporized the steel tower that held the bomb and left a crater of glassed sand beneath it. Observers miles away felt the heat on their faces. The shockwave rippled through the desert air, carrying with it both triumph and dread. The weapon worked far beyond anyone's imagination. The energy released from that single explosion came from the splitting of mere grams of matter. Yet it held the destructive power of 20,000 tons of TNT. The impossible had become real. Weeks later, the world witnessed what that power meant when it was used in war. Hiroshima and Nagasaki were reduced to ruins within seconds. Tens of thousands of lives vanished in a blinding instant, and countless more suffered in the aftermath. The scale of destruction defied comprehension. Entire cities became wastelands of silence and ash. Those who survived spoke of shadows burned into walls, of skies raining black dust, of a world where morning light brought death instead of warmth.
Yes, adjusting
The
the flow
bomb
valve
had not
now.
only ended
It should
a war,
stabilize the
it had
cascade.
introduced the planet to a new kind of fear. Humanity had entered the atomic age. In the wake of the bombings, the world was forced to reckon with what it had unleashed. The development of nuclear weapons was more than a military breakthrough. It was a profound shift in human consciousness. For the first time in history, mankind possessed the ability to annihilate itself entirely. Nations realized that power had reached a new threshold, one where victory could mean extinction. The Cold War that followed was not just a political struggle, but a psychological one, defined by the constant threat of mutual destruction. The doctrine of deterrence emerged, built on the grim logic that possessing these weapons might prevent their use. It was a paradox that would dominate global politics for decades. The development of nuclear weapons also reshaped science itself. The line between discovery and destruction
The enrichment
blurred.
level is higher than we
Scientists
anticipated.
who once sought knowledge for its
Look at the
own
count rate,
sake
it's spiking.
found
We need to
themselves
secure
part
this
of a
now.
moral debate that
The count
continues
rate
to this
confirms the
day.
enrichment level
Was
right
it
here.
justified?
Yes, I see it.
Could
The
it have
activity
been
is
avoided?
intensifying near the edge.
Many of
We
those
should
who
log this
worked on the
immediately.
Manhattan Project later became advocates for arms control and disarmament. They understood the magnitude of what they had created, a power that could either protect or obliterate civilization. Yet, amid the fear and regret, the atomic revolution also fueled new hopes. Nuclear energy, the peaceful counterpart to nuclear weapons, promised to bring electricity to millions, to power cities without smoke or coal. The same principles that had created destruction also offered progress. This duality, creation and devastation, became the defining characteristic of the nuclear age. It was a reminder that every great scientific advance carries with it both promise and peril, and that the true measure of humanity lies not in what it can create, but in how it chooses to use that creation. The development of nuclear weapons stands as a turning point, not only because of its scientific magnitude, but because it forever changed how humanity perceives itself. Before 1945, wars were brutal but limited. Afterward, they became existential. The atom bomb forced every nation, every leader, and every citizen to confront the limits of power and the fragility of life. It redefined strategy, diplomacy, and ethics. It reshaped our literature, our art, our fears, and even our faith. The mushroom cloud became a symbol not of victory, but of warning, a reminder that knowledge without wisdom can lead to ruin. The story of nuclear weapons is ultimately the story of humanity's reach, our unending quest to understand the universe, and our equally profound struggle to live responsibly within it. What began as curiosity about the smallest parts of matter ended as a test of the human spirit. In that test, we discovered both the brilliance of our intellect and the darkness of our ambition. The development of nuclear weapons
readings are
marked a
spiking,
turning
sir.
point in
We're
history
going critical. Pull
because
the
it
switch.
revealed a truth that still haunts us. that in mastering the atom, we also uncovered the power to destroy ourselves. The aftermath of the bombings of Hiroshima and Nagasaki did more than end a war. It set the stage for a global reckoning. Cities lay in ruins, survivors faced unimaginable injuries, and entire cultures were forced to confront the reality that human beings had unlocked a power once thought to belong solely to the divine. In the weeks, months, and years that followed, historians, politicians, and scientists wrestled with a new truth. The landscape of conflict had forever changed. Wars could no longer be measured merely by armies and territory. They now encompassed the potential for annihilation on an unprecedented scale. For the first time, the phrase total war took on a literal meaning. The atom, once the subject of abstract theorizing, had become a tangible and terrifying instrument of global consequence. The consequences of this new weapon extended beyond the immediate destruction. The psychological impact on the world
we have
was
stabilization
profound.
at 3.5
Governments
microseconds.
realized that
Data
possessing
logged.
nuclear weapons
Sequence logged.
was not
We are
merely
green.
a military advantage. It became a symbol of technological and political supremacy. Nations raced to understand, replicate, and, if possible, surpass the power that the United States had demonstrated. This urgency gave rise to the Cold War, an era defined by tension, espionage, and the looming threat of nuclear confrontation. The United States and the Soviet Union, in particular, engaged in an arms race that would span decades, each side stockpiling weapons of incredible destructive potential. Cities across the globe built bomb shelters, families practiced evacuation drills, and the constant specter of annihilation became part of daily life. Humanity had entered a new epoch, where survival depended not only on diplomacy and politics, but also on a terrifying technological deterrent. Science itself was forever altered by the development of the bomb. The success of the Manhattan Project demonstrated the capacity of organized scientific enterprise to achieve monumental goals. Large-scale collaboration between physicists, chemists, engineers, and military planners revealed that science could operate at speeds and scales previously unimaginable. At the same time, the project highlighted a moral dimension to scientific work that could no longer be ignored. Researchers were no longer isolated scholars in ivory towers. Their discoveries carried consequences of life and death for millions. The atom bomb forced a reconsideration of the role of science in society. It asked a difficult question. Should knowledge exist purely for exploration, or does the power it enables require ethical oversight and responsibility? These questions continue to resonate in fields as diverse as biotechnology, artificial intelligence, and space exploration, echoing the lessons learned from the earliest days of nuclear research. The social and cultural repercussions of nuclear weapons were equally profound. Art, literature, and cinema began to grapple with the existential implications of atomic power. Writers imagined post-apocalyptic worlds. Films visualized mushroom clouds and cities reduced to ash. And philosophical debates emerged over the morality of wielding such unprecedented force. For the first time in human history, the potential for instantaneous, large-scale destruction influenced cultural expression on a global scale. Nuclear weapons became more than instruments of war. They became symbols of the human capacity for both ingenuity and self-destruction. They inspired fear, awe, and a profound contemplation of humanity's place in the universe. The strategic implications of nuclear weapons transformed global politics. The mere existence of such destructive capability necessitated new approaches to international relations. Diplomacy became intertwined with technological supremacy. Treaties such as the Nuclear Non-Proliferation Treaty, NPT, and arms control agreements like the Strategic Arms Limitation talks, SALT, emerged to address the delicate balance of power. Nations recognized that a single misstep could trigger devastation on a global scale, making caution and negotiation vital to survival. The doctrine of mutually assured destruction, MAD, became the cornerstone of international security strategy, a principle that paradoxically depended on the threat of total annihilation to maintain peace. Nuclear weapons redefined warfare from a tactical and territorial exercise into a philosophical and existential consideration, requiring leaders to weigh not only the immediate outcomes of conflict, but the long-term survival of civilization itself. The development of these weapons also had profound ethical implications. Scientists and policymakers had to confront questions that transcended immediate military necessity. Was it morally permissible to end a war at the cost of civilian lives? Could humanity control a force capable of destroying entire populations and ecosystems? These ethical dilemmas persist today, influencing debates on nuclear proliferation, disarmament, and the role of technology in society. The atomic bomb forced a confrontation between human ambition and human responsibility, a tension that continues to shape policy, science, and philosophy. In grappling with the power to obliterate, humanity was forced to confront the consequences of its intellect, the realization that progress, unchecked by moral reflection, could lead to catastrophe. Scientific understanding of nuclear energy also opened pathways to peaceful applications, illustrating the dual nature of technological discovery. Nuclear reactors provided energy capable of powering cities without reliance on fossil fuels, a testament to the constructive potential of the same principles that had been used for destruction. Medicine benefited from advances in radiology and radiation therapy. Yet, these benefits were always accompanied by the shadow of risk. Nuclear accidents, such as Chernobyl and Fukushima, underscored the need for caution, regulation, and ethical oversight in the application of such potent technologies. The development of the bomb had created not only a weapon, but a paradigm for understanding the consequences of knowledge applied without restraint. The atomic age also reshaped collective human consciousness. The realization that the species could wipe itself out with a single technological advance created a new awareness of vulnerability. Global institutions, such as the United Nations, found themselves compelled to address questions of war, peace, and security in a new context. Civil defense initiatives, public education on nuclear threats, and international negotiations reflected a world forced to confront the reality of its own capabilities. Humanity's identity shifted. No longer merely masters of the planet, humans were now custodians of a power that could end their existence. The bomb became a mirror, reflecting both the brilliance and the dangers of human ingenuity. The long-term implications of the bomb's development continue to unfold. Nations around the world maintain arsenals, debate the ethics of deterrence, and study historical examples to understand the complex interplay between science, politics, and morality. The legacy of the Manhattan Project is not simply a historical footnote, but a living influence on policy, culture, and education. Lessons from that era inform contemporary discussions on emerging technologies, from artificial intelligence to biotechnology, reminding humanity that with every leap in understanding comes a responsibility that cannot be ignored. The development of nuclear weapons was not only a turning point in military history, but also a turning point in the evolution of human thought, ethics, and global consciousness. In reflecting on this era, it becomes clear that the atomic bomb was more than a tool of war. It was a symbol of human potential and peril. The achievement represented the pinnacle of scientific collaboration and ingenuity, yet it also carried consequences of unparalleled magnitude. Humanity was forced to reckon with its ability to create and destroy on a scale that had never before existed. The bomb served as both a warning and a reminder. Knowledge is powerful, and the consequences of its application are profound. In the decades since 1945, the shadow of the atomic age has shaped international relations, ethical debates, scientific inquiry, and cultural imagination. It remains a defining chapter in human history, marking the moment when the world recognized that its fate was intertwined with the knowledge it possessed and the choices it made. Ultimately, the development of nuclear weapons marked a turning point because it exposed a fundamental truth. Human innovation carries responsibilities equal to its capabilities. The atom bomb was the first tangible demonstration that science could alter the course of civilization itself. It forced society to confront questions of ethics, governance, and survival that had never arisen in human history. In harnessing the power of the atom, humanity glimpsed both its own potential for greatness and its capacity for destruction. That duality, revealed in a blinding flash over Hiroshima and Nagasaki, continues to define the modern world. The development of nuclear weapons is not merely a historical milestone. It is a lens through which to understand the relationship between knowledge, power, and responsibility. A reminder that decisions of today shape the possibilities and dangers of tomorrow. During the height of World War II, the world stood at the precipice of a technological revolution that would forever alter the nature of warfare. The scientific community, driven by both urgency and curiosity, was working in unprecedented secrecy to unlock the power hidden within the atomic nucleus. It was a time of extraordinary innovation, but also of profound ethical uncertainty. Within this context, two radically different bomb designs emerged, each representing a unique path toward harnessing the enormous energy released by nuclear fission. These two approaches, the gun-type and the implosion type, would come to define not only the weapons themselves, but also the very strategy of how nuclear energy could be controlled and directed for destructive purposes. The gun-type design was, in many ways, the more straightforward of the two. Its conceptual simplicity was appealing. Combine two subcritical masses of fissile material rapidly, and a chain reaction would occur, releasing unimaginable amounts of energy in a fraction of a second. The scientists and engineers who worked on this design were inspired by principles that were easy to visualize, almost mechanical in nature. The weapon relied on a precise arrangement in which one piece of uranium-235 would be propelled into another using conventional explosives. This gun mechanism ensured that the two masses would collide with sufficient speed and accuracy to surpass the critical mass threshold, the point at which a self-sustaining nuclear chain reaction could begin. The beauty of this approach lay in its simplicity. There were no complex detonations surrounding the core, no intricate timing systems, no need for the extraordinary precision demanded by other designs. The gun-type bomb was a direct and elegant method of converting nuclear potential into explosive power. Yet simplicity came at a cost. The gun-type bomb was limited by the materials it could use. Uranium-235, the fissile isotope required for this method, was rare and difficult to isolate. Separating uranium-235 from the more abundant uranium-238 required massive industrial efforts involving electromagnetic separation and gaseous diffusion. technologies that had never before been employed on such a
The
scale.
readings on panel 7
The sheer
are
scale
dropping
of
slightly.
production became
Yes,
a
adjusting the
defining
flow valve
characteristic
now.
of the
It should
Manhattan
stabilize
Project.
the cascade.
As thousands of workers labored to produce enough fissile material to make even a single weapon viable. Beyond material scarcity, the design itself had physical limitations. Its explosive yield, while devastating, could not reach the levels possible with other methods, and the risk of pre-detonation or failure, though low, still existed. In the end, the gun-type approach was a solution that combined scientific ingenuity with practical constraints, balancing theoretical understanding with the realities of wartime production. In contrast, the implosion-type design represented a more sophisticated and technically demanding approach. While the gun-type relied on a simple collision, the implosion bomb sought to compress a subcritical mass into a supercritical state through symmetrical detonation. In essence, the fissile material, typically plutonium-239, was surrounded by a carefully engineered arrangement of conventional explosives. When detonated, these explosives compressed the core uniformly from all sides, increasing its density and causing a chain reaction powerful enough to create a massive explosion. The idea was elegant in principle, but extraordinarily difficult in practice. Achieving perfect symmetry in detonation was a challenge that had never been attempted before on such a scale. Even a slight asymmetry could cause the reaction to fizzle or result in partial detonation, wasting both the material and the effort of countless scientists and engineers. Yet, despite these challenges, the implosion design offered significant advantages. Plutonium-239 was more readily produced in nuclear reactors than uranium-235, and the implosion method allowed for a more efficient and powerful detonation, unlocking energy levels far beyond the capability of the gun-type bomb. The development of the implosion-type bomb demanded a level of scientific collaboration and innovation that was
We have
unprecedented.
stabilization at 3.5
Mathematicians,
microseconds.
physicists,
Data
and
logged.
engineers
Sequence
worked
locked.
together to
We
model
are
the
green.
complex behavior of explosives, shock waves, and nuclear materials. Precision became paramount. Detonation timing had to be controlled to fractions of a microsecond, and the geometrical configuration of explosives and the plutonium core had to be perfected. Scientists conducted extensive tests, including experiments with high explosives and non-fissile cores, to understand how shock waves could be shaped and focused. The challenges were immense, but the rewards were equally great. The implosion bomb promised a new level of destructive power and reliability, a weapon that could achieve the full potential of plutonium without the material limitations of the gun-type design. While the gun-type bomb was deployed first in Hiroshima, it was the implosion type that would follow in Nagasaki. The choice reflected not only the availability of fissile material, but also the strategic desire to test and demonstrate both methods of delivering nuclear force. The contrast between the two designs was stark. One relied on direct kinetic force, the other on sophisticated compression. One depended on scarce uranium, the other on more accessible plutonium. The gun-type represented simplicity and reliability. The implosion type represented complexity and greater destructive potential. Together, they illustrated the dual paths that scientific ingenuity could take when applied to the art of warfare, highlighting both the possibilities and the risks inherent in manipulating fundamental forces of nature. Beyond their technical differences, these two bomb designs also shaped the way nuclear weapons would be understood and developed in the years that followed. The gun-type bomb demonstrated that nuclear fission could be weaponized with relatively simple mechanics,
This
offering a
technological
proof
power
of
demands a
concept
moral
that was both
response.
terrifying
Total and universal
inspiring.
disarmament is the only
The
answer.
implosion-type bomb pushed the boundaries of engineering, illustrating the potential for innovation when scientists confronted seemingly insurmountable challenges. In combination, these designs established the framework for modern nuclear strategy, influencing not only the construction of future weapons, but also the geopolitical calculus that would dominate the 20th century. Nations recognized that mastery over the atom was not solely a matter of theoretical physics, but also of materials, engineering, and the ability to execute extraordinarily precise operations under pressure. The historical significance of these two bomb designs cannot be overstated. They represent more than the mechanics of detonation. They symbolize the convergence of science, technology, and human ambition during one of the most consequential periods in history. The gun-type and implosion-type bombs were milestones in understanding how nuclear fission could be harnessed, demonstrating both the possibilities of human creativity and the destructive power it could unleash. In their development, one sees a microcosm of the challenges faced by all who seek to apply theoretical knowledge to practical ends. The tension between simplicity and complexity, reliability and power, scarcity and abundance, and above all, the ethical responsibility that accompanies the creation
The extraction
of
phase is
unprecedented
complete.
force. The story
Levels
of
are
the gun,
stable.
type and
Proceed with the final
implosion,
transfer.
type bombs is, in essence, a story of human ingenuity confronting the unknown. It is a tale of trial and error, of mathematical modeling and explosive testing, of sleepless nights and relentless pursuit of perfection. It is also a story of choices, of deciding which path to follow when the stakes could not be higher. Both designs achieved their ultimate goal, demonstrating that the atom could be split to release energy of unimaginable magnitude, yet each did so in a way that reflected a distinct philosophy of engineering and science. One was straightforward, almost mechanical in its approach. The other was intricate, demanding, and elegant in its precision. Both were necessary, both were terrifying, and both would leave an indelible mark on human history. In the end, these two designs illustrate a profound truth about technological progress. Innovation often takes multiple forms, and the path from discovery to application is rarely linear. The gun-type and implosion-type bombs were born of necessity, but they were also shaped by the imagination, skill, and determination of the scientists who built them. They represent not only the power of the atom, but also the power of human intellect, demonstrating how understanding, creativity, and persistence can transform abstract theory into tangible reality. Yet, as history would show, this power comes with a cost. The legacy of these designs is inseparable from the destruction they caused and the ethical questions they raised. Questions that continue to shape the discourse on nuclear weapons, strategy, and global responsibility to this day. The development and deployment of the gun, type and implosion, type bombs revealed not only the ingenuity of scientific minds, but also the complexities of applying theoretical knowledge under the pressures of wartime urgency. Each design reflected a different philosophy of problem solving and engineering. The gun-type bomb, with its simplicity and mechanical reliability, demonstrated that a nuclear explosion could be achieved without extraordinary precision, relying instead on straightforward kinetic energy to initiate a chain reaction. The implosion-type bomb, by contrast, required meticulous calculation, experimentation, and coordination.
Yes, I did.
Its successful
It's a boat.
creation underscored the capacity of human innovation to master phenomena that, on the
Pressure's
surface,
dropping. Steady
seemed
now.
unpredictable and uncontrollable. The contrast between the two designs illuminated the spectrum of human engineering, from the straightforward to the sophisticated, from the predictable to the delicate. The differences between the two bombs were also tied intimately to the types of fissile material they employed. The gun-type bomb used uranium-235, a material that was painstakingly separated from uranium-238 using complex, labor-intensive processes. The implosion-type bomb, on the other hand, utilized plutonium-239, a byproduct of nuclear reactors that, although easier to produce in sufficient quantities, presented new challenges. Plutonium-239 is more prone to spontaneous neutron emission, making the gun-type method unworkable with this material. The implosion technique was therefore a direct response to these limitations, showing how scientific and engineering ingenuity could overcome material constraints. These differences highlight the way that the properties of the atomic elements themselves shaped the trajectory of human technological development. Scientists did not simply impose their will on nature. They adapted to it, devising methods that worked within the bounds of physics and chemistry. The engineering challenges of the implosion design were immense. High explosives had to be arranged with perfect symmetry to compress the plutonium core evenly. Any irregularity could result in a fizzle, a failed detonation that would waste both material and effort. To achieve this, scientists and engineers conducted countless tests with surrogate materials to model shock, wave behavior, and compression dynamics. Precision timing systems were developed to synchronize multiple detonators to within microseconds, ensuring the implosion occurred uniformly. This level of exactitude was unprecedented, pushing the boundaries of what was considered possible in both physics and engineering. The implosion bomb was not merely a weapon. It was a triumph of precision science and collaborative problem solving, a testament to human persistence under the most intense pressure imaginable. The first successful test of the implosion design at the Trinity site in July 1945 demonstrated the immense potential of this method. Unlike the gun-type bomb, whose explosion was primarily dependent on the straightforward collision of uranium masses, the implosion bomb converted a small amount of plutonium into an energy release of staggering magnitude through carefully orchestrated compression. The brilliance of the design lay in its efficiency. More energy could be extracted from less material, making it both powerful and practical. This success marked a turning point in the development of nuclear weapons, validating the theoretical calculations, engineering innovations, and collaborative problem-solving efforts that had consumed the focus of thousands of scientists and engineers for years. The implosion bomb represented a level of technical sophistication that would inform future nuclear weapons programs worldwide. Despite the technical distinctions between the two designs, both shared a fundamental principle. They relied on a rapid, uncontrolled chain reaction of nuclear fission. In each case, the objective was to achieve critical mass quickly enough that the reaction would release its energy explosively before the bomb disassembled itself. This principle underscored the delicate balance of science and engineering involved in nuclear weapons development. While the gun-type bomb relied on velocity and collision, the implosion bomb relied on compression and symmetry. Both approaches revealed the underlying unity of nuclear physics, demonstrating that different methods could achieve the same end through the clever manipulation of energy and matter. This duality, two methods achieving similar destructive results, would influence strategic thinking, technological development, and the ethical considerations surrounding the use of nuclear weapons. The use of both bomb designs in wartime conditions further highlighted the practical considerations that influenced their development. The gun-type bomb dropped on Hiroshima represented the simpler path, one that could be relied upon to function with minimal risk of failure. The implosion-type bomb, used in Nagasaki, represented the culmination of years of complex experimentation and engineering. Each city's experience underscored the consequences of these designs. The sheer destructive power of nuclear energy, whether released through straightforward means or through highly sophisticated engineering, the contrast between the two deployments illuminated not only the technological differences, but also the logistical and strategic thinking behind wartime nuclear decisions. Decisions about which design to use, when, and where reflected a convergence of scientific understanding, engineering capability, and military strategy. The legacy of the Gun-Type and Implosion-type bombs extends far beyond the historical events of 1945. They set the stage for decades of nuclear research, proliferation, and strategy. The Gun-Type design demonstrated that nuclear weapons could be constructed in a relatively straightforward manner, influencing early Cold War considerations and encouraging the development of uranium-based arsenals. The implosion-type design, meanwhile, set a precedent for the development of more sophisticated and powerful weapons, including thermonuclear devices. The dual paths represented by these bombs also offered insight into the relationship between science, materials, and engineering in the creation of weapons. Technical feasibility, material availability, and precision engineering all became critical factors in the design and deployment of nuclear arsenals worldwide. Beyond their technical and strategic significance, the development of these two designs also shaped ethical and philosophical discussions. Scientists who contributed to the Manhattan Project were confronted with the consequences of their work almost immediately. The successful implementation of both designs forced a confrontation with the moral implications of creating devices capable of unprecedented destruction. The Gun-Type bomb was relatively simple, but its existence prompted reflection on whether the ability to create a weapon so easily should be exercised. The implosion-type bomb, with its sophisticated design, illustrated that human ingenuity could harness even the most complex natural forces for destructive ends. Together, these weapons challenged humanity to consider not only what could be done, but what should be done, raising questions that continue to influence debates on nuclear ethics, deterrence, and disarmament. In the broader context, the two designs also demonstrated the ways in which scientific innovation can follow multiple paths simultaneously. They illustrate that even when the goal is singular, harnessing nuclear energy for explosive power, the approach may vary depending on the constraints of materials, technological capability, and ingenuity. The Gun-Type bomb emphasized simplicity, predictability, and immediate practicality, while the implosion type emphasized sophistication, efficiency, and maximal power. Both paths were valid, each with its own advantages and limitations. This duality provides a powerful lesson for understanding technological development in general. Innovation is rarely linear, and multiple solutions can coexist, each reflecting the interplay of science, engineering, and circumstance. Ultimately, the Gun-Type and Implosion-type bombs represent a watershed moment in human history, not only in terms of military capability, but also in terms of the intellectual and ethical dimensions of technological progress. Their development required unprecedented collaboration, cutting-edge research, and the resolution of complex scientific problems under extreme time pressure. They revealed both the possibilities and dangers inherent in applying theoretical knowledge to practical ends. The two designs also set the stage for the nuclear strategies and doctrines that would dominate international relations for the rest of the 20th century and beyond. By examining the creation and deployment of these bombs, one gains insight into the intricate dance between scientific discovery, engineering ingenuity, and the moral responsibility that accompanies the power to alter the fate of humanity. In conclusion, the story of the Gun-Type and Implosion-type bombs is a story of human intellect and ambition confronting the most fundamental forces of nature. It is a tale of parallel paths toward the same end, one path emphasizing simplicity and reliability, the other sophistication and efficiency. It is also a story of consequences, the destruction they wrought, the ethical debates they inspired, and the global strategies they shaped. The emergence of these two bomb designs during World War II stands as a defining chapter in history, illustrating the dual nature of scientific progress, the ability to create solutions that are both brilliant and terrifying, practical and devastating. Together, they offer a lens through which to understand the complex interplay of science, technology, and human responsibility, a lens that continues to inform the modern world. At the heart of every nuclear weapon lies a singular, terrifying principle: the ability to initiate a chain reaction so rapid and uncontrollable that it releases the energy of the atom almost instantaneously. Both the Gun-Type and the Implosion-type bombs, though different in design and engineering, relied on this same fundamental process. Nuclear fission occurs when the nucleus of a heavy atom, such as uranium-235 or plutonium-239, splits into smaller fragments after absorbing a neutron. This splitting releases a tremendous amount of energy, measured not in conventional explosives, but in the conversion of mass itself into energy, following the principles Einstein outlined in his famous equation E equals mc2. The true power of these weapons stems not merely from the fission of individual atoms, but from the cascading chain reaction that occurs when neutrons released by one fission event strike other nuclei, perpetuating an exponential sequence of reactions. The Gun-Type bomb achieved this chain reaction through a deceptively simple mechanism. A subcritical mass of uranium-235 was fired into another subcritical mass using conventional explosives. Once the two pieces combined, the assembly reached a supercritical state. The critical mass threshold was surpassed almost instantly, allowing neutrons to collide with uranium nuclei in a self-sustaining and accelerating reaction. Within microseconds, an immense quantity of energy was released, manifesting as heat, blast, and radiation. The process was irreversible. Once the reaction began, it could not be stopped, and the bomb effectively destroyed itself while releasing the full potential of the fissile material. This simplicity masked the complexity of controlling the timing and velocity necessary to prevent pre-detonation and ensure maximum energy output. The Implosion-type bomb approached the same goal through a different, more sophisticated method. Instead of propelling two pieces together, scientists surrounded a plutonium-239 core with precisely shaped explosive lenses. When detonated, these explosives compressed the core uniformly from all directions, dramatically increasing its density and forcing it into a supercritical state. By carefully synchronizing the detonation of multiple explosive charges, the implosion method maximized the efficiency of the chain reaction, ensuring that a far greater proportion of the material underwent fission. The implosion design demonstrated that the chain reaction was not only a matter of having sufficient fissile material, but also of controlling the geometry and timing of the assembly to achieve rapid, uncontrolled release of energy. Both designs illustrate a central truth about nuclear weapons. The destructive power of the atom depends on speed, precision, and the exponential nature of the fission chain reaction. Neutrons multiply with each fission event, creating a feedback loop that turns microscopic atomic interactions into forces capable of leveling cities. The process is fundamentally uncontrollable once initiated, and the difference between controlled nuclear reactions in reactors and the uncontrolled explosions of bombs lies in this rapidity and self-amplifying behavior. In the end, whether through a simple gun-type collision or a complex
The readings
implosion,
on panel 7
the
are
goal
dropping
was
slightly.
identical.
Yes,
To harness
adjusting
the
the flow
atom's
valve
energy
now.
in a
It should
fraction of a
stabilize the
second,
cascade.
unleashing a force that would forever alter human history. The story of nuclear weapons is inseparable from the materials at their core. Uranium-235 and plutonium-239 are not merely elements. They are the keys that unlock the immense energy of the atom. The gun-type bomb relied on uranium-235, a rare isotope of uranium that occurs in nature only in trace amounts. Uranium-235 is fissile, meaning it can sustain a chain reaction when struck by a neutron. However, it is found alongside the far more abundant uranium-238, which is not easily fissioned. Extracting enough uranium-235 for a weapon required enormous industrial effort, employing techniques such as gaseous diffusion and electromagnetic separation. These processes were slow, costly, and required vast resources, yet they were essential because the gun-type method demanded a material that could achieve supercriticality through a relatively simple collision of two subcritical masses. The uranium-235 used in this design had to be highly enriched to ensure that the chain reaction would occur reliably, making the material itself a critical limiting factor in the production and deployment of this type of bomb. Plutonium-239, in contrast, was the central material for the implosion-type bomb, a choice driven by both necessity and opportunity. Plutonium-239 does not occur in significant quantities in nature, but can be produced in nuclear reactors by irradiating uranium-238 with neutrons. This allowed scientists to generate the fissile material on a larger scale than was practical for uranium-235. Plutonium-239 has properties that made the gun-type method impractical, primarily its tendency for spontaneous neutron emission, which could cause premature detonation if two subcritical masses were simply fired together. To address this, the implosion design was developed. By surrounding a plutonium core with precisely shaped explosive charges, scientists could compress it to a supercritical state in microseconds, ensuring that the chain reaction began at exactly the right moment. The combination of plutonium-239 and the implosion method made possible a more efficient and powerful explosion, one that could release far more energy than the gun-type uranium bomb while using less material. The choice of fissile material was not merely a technical detail. It shaped the entire design, production, and deployment process of nuclear weapons. Uranium-235 required massive industrial separation plants, painstaking refinement, and careful handling to avoid contamination or accidental criticality. Plutonium-239, produced in reactors, demanded the invention of complex chemical separation techniques and a deep understanding of reactor physics. The properties of these isotopes dictated the design constraints, the engineering solutions, and even the strategy for using the bombs in wartime conditions. Without uranium-235, the gun-type bomb could not exist. Without plutonium-239, the implosion bomb would have remained impossible. Each material dictated the method of unleashing the atom's power, demonstrating the intimate relationship between nuclear physics and practical engineering. Ultimately, uranium-235 and plutonium-239 are more than scientific curiosities. They are symbols of the dual paths humanity followed to harness atomic energy for destruction. One path emphasized rarity, simplicity, and direct collision. The other emphasized availability, precision, and compression. Together, they illustrate the marriage of materials science and engineering creativity that made the atomic bomb a reality. The story of these isotopes is a story of how humanity learned not just to observe the atom, but to control it, for better or for worse, shaping the course of history in ways no one could have fully anticipated. The gun-type nuclear bomb represents one of the simplest concepts in the history of atomic weapons, yet its apparent simplicity masked significant practical challenges. At its core, the gun-type design was based on a straightforward idea: bring two subcritical masses of uranium-235 together at high speed to achieve a supercritical mass capable of sustaining a rapid chain reaction. The mechanism resembled the firing of a cannon, with one piece of uranium propelled into another using conventional explosives. The collision of these masses initiated the fission process, releasing an extraordinary amount of energy in a fraction of a second. Its simplicity made it easier to conceptualize, test, and deploy compared to other designs. Engineers and scientists could focus on achieving reliable firing and alignment, rather than navigating the complex physics of compression or implosion. In many ways, this approach exemplified direct and practical engineering. Minimal moving parts, clear mechanics, and a predictable outcome, provided the material requirements were met. However, the design's simplicity also exposed its inherent limitations. The most significant constraint was the need for highly enriched uranium-235. Uranium-235 is exceedingly rare in nature, representing less than 1% of natural uranium. Extracting it from the more abundant uranium-238 required vast industrial efforts, involving methods such as gaseous diffusion and electromagnetic separation. These processes consumed enormous amounts of energy, time, and resources, and limited the quantity of fissile material available for weapons production. Because of this scarcity, only a small number of gun-type bombs could be manufactured during the wartime period, restricting their practical use and overall impact. Another limitation lay in efficiency. Although the gun-type design could reliably achieve detonation, it was not capable of releasing the maximum energy possible from its uranium-235. Only a fraction of the fissile material underwent fission before the bomb destroyed itself, limiting the explosive yield relative to the amount of material used. This inefficiency meant that larger quantities of uranium were required to produce each bomb, further exacerbating the scarcity problem. In contrast, other designs, such as the implosion type, could achieve greater energy release with less material due to more efficient compression of the fissile core. The gun-type method, while mechanically simpler, could not rival this level of sophistication or yield. The simplicity of the gun-type bomb also made it more predictable in behavior, but offered little room for innovation once the basic mechanism was established. It relied entirely on a linear approach, leaving no opportunity to exploit advanced techniques like explosive lensing or precise timing to increase efficiency. While this made it more reliable, it also limited the weapon's adaptability and scalability for future needs. The combination of material scarcity and limited energy output meant that, while the gun-type design was historically significant, it represented an early stage in the evolution of nuclear weapons rather than the pinnacle of destructive capability. Ultimately, the gun-type bomb illustrates a paradox in technological innovation. Simplicity can offer reliability and clarity, yet it may also impose strict limits on efficiency and scalability. The design's reliance on scarce uranium-2, 135, its modest yield relative to potential energy, and its inability to evolve beyond its basic mechanics highlight both the strengths and constraints of straightforward engineering approaches in the context of nuclear physics. It stands as a reminder that even elegant solutions can be bounded by the laws of nature and the availability of critical resources, shaping both their practical application and historical impact. The implosion-type bomb represents one of the most intricate and ambitious achievements of wartime science. Unlike the gun-type design, which relied on a simple collision of two subcritical masses, the implosion bomb used a carefully engineered system to compress a plutonium-2, 139 core into a supercritical state. The principle behind this method was elegant but extraordinarily difficult to execute. A sphere of fissile material, initially subcritical, had to be surrounded by a precise arrangement of high explosives. When detonated simultaneously, these explosives generated an inward, moving shockwave, compressing the plutonium core uniformly from all sides. The compression increased the density of the material, lowering the critical mass threshold and initiating a rapid, self-sustaining nuclear chain reaction. This approach allowed a far greater proportion of the material to undergo fission, releasing energy that was significantly higher than that of the simpler gun-type design. The complexity of the implosion method arose from multiple technical challenges. First, the detonation had to be perfectly symmetrical. Any deviation in timing or explosive configuration could cause the core to compress unevenly, resulting in a partial failure or fizzle, rather than a full nuclear detonation. Achieving this level of precision required innovations in explosive lensing and detonation synchronization, technologies that had never been used on such a scale. Scientists developed specialized detonators capable of firing simultaneously within microseconds, and explosive lenses were meticulously shaped to focus the blast waves toward the core. Every aspect of the bomb's geometry and timing was critical, and even the smallest miscalculation could render the weapon ineffective. Despite the engineering challenges, the implosion method offered clear advantages. Plutonium-2, 139, the material used in this design, was more readily produced in nuclear reactors than uranium-2, 135, making it a practical choice for large-scale weapon production. More importantly, the implosion design maximized the efficiency of the chain reaction, ensuring that a higher percentage of fissile material underwent fission before the bomb disassembled itself. The result was a more powerful explosion with less material compared to the gun-type bomb, demonstrating the effectiveness of precision engineering combined with deep scientific understanding. The success of the Trinity test in July 1945 validated these efforts, confirming that the implosion design could reliably deliver its full destructive potential. The implosion-type bomb also influenced the future of nuclear weapons development. Its design demonstrated that complexity, while risky and resource-intensive, could yield superior results when carefully managed. It provided a model for subsequent nuclear devices, including thermonuclear weapons, which relied on similar principles of compression and staged detonation. The implosion method illustrated that achieving maximum destructive efficiency required not only understanding the physics of nuclear fission, but also mastering the intricacies of explosive engineering, timing, and materials science. This combination of theoretical insight and practical skill represented a milestone in scientific and technological achievement. Ultimately, the implosion method exemplifies the paradox of nuclear innovation. It was far more difficult to build than the gun-type design, yet it was also more reliable, efficient, and devastating. It showcased humanity's ability to translate abstract principles of nuclear physics into controlled, large-scale energy release. While the gun-type bomb demonstrated that the atom could be split to produce an explosion, the implosion bomb revealed the full potential of nuclear power, harnessing it with precision and maximizing its destructive force. In doing so, it reshaped the possibilities of warfare and highlighted the extraordinary ingenuity and responsibility required to wield the most powerful force ever created by humankind. The creation and deployment of nuclear weapons marked a turning point in human history, not only because of the destruction they could unleash, but because of the profound ways they altered warfare, ethics, and global politics. For the first time, humanity possessed a tool capable of annihilating entire cities in a single instant. Hiroshima and Nagasaki became grim proof of this new reality, demonstrating the unprecedented power of these weapons and leaving a lasting scar on the human imagination. The sheer scale of destruction forced nations, leaders, and citizens to confront a question that had never before arisen in warfare: how to wage conflict in an era when the cost could extend to total human annihilation. Traditional notions of battle, victory, and strategy no longer applied. The atomic bomb rendered entire populations vulnerable and created a paradigm in which deterrence became as important as direct military action. The ethical ramifications of nuclear weapons were immediate and profound. Scientists, many of whom had worked on the Manhattan Project with patriotic intent, faced the moral consequences of their creation. They had transformed theoretical physics into a tool of mass destruction, and the lives lost in Hiroshima and Nagasaki weighed heavily on their consciences. Questions arose about the justification of targeting civilian populations, the balance between ending a war quickly and preserving life, and the broader responsibility of wielding such devastating power. These ethical dilemmas did not remain confined to the scientists. They reverberated throughout governments, religious institutions, and intellectual communities, sparking debates that continue to this day. The atomic bomb forced humanity to consider the relationship between technological capability and moral responsibility in ways never previously imagined. On a strategic level, nuclear weapons transformed global politics. The post-war world quickly entered the Cold War, an era defined by tension, espionage, and the constant threat of nuclear confrontation. Nations understood that possessing these weapons conferred enormous influence, and the arms race between the United States and the Soviet Union shaped international relations for decades. The doctrine of mutually assured destruction emerged, based on the grim logic that the certainty of retaliation would prevent either side from initiating nuclear war. In this new geopolitical landscape, power was no longer measured solely in terms of territory, armies, or resources, but in the ability to deliver mass destruction instantaneously. Diplomacy, treaties, and negotiation all became intertwined with nuclear strategy, fundamentally changing how states interacted and perceived threats. The existence of nuclear weapons also influenced broader societal and cultural perspectives. Art, literature, and film began to grapple with the specter of annihilation, reflecting widespread public anxiety about a world in which human civilization could be obliterated in moments. Nuclear weapons became symbols not only of technological mastery, but also of the fragility of life and the weight of human responsibility. They highlighted the dual nature of scientific advancement, the capacity for extraordinary achievement, and the potential for catastrophic consequences. Humanity was forced to recognize that progress in knowledge and technology was inseparable from ethical and political considerations. Ultimately, the creation and use of nuclear weapons reshaped the very framework of modern existence. Warfare, ethics, and global politics were forever altered, as nations learned that the stakes of conflict now extended to the survival of civilization itself. The atomic bomb demonstrated both the power and the peril of human ingenuity, leaving an enduring legacy that continues to influence scientific research, military strategy, international relations, and moral philosophy. It was a moment that redefined what it meant to hold power in the modern world, a reminder that the tools we create can shape not only the course of history, but the very nature of human responsibility.